So we've been talking about the image and the kernel of linear transformations. And one of the things that we learned was that if A is a matrix, then the image of A is spanned by the columns of A. And this is simply because of the way matrix multiplication works, that A times X is always a linear combination of columns of A. But if you just write down all the columns of A, that may not be the most efficient description of the image. For example, if we look at this matrix, you could say that any vector in the image of A is a linear combination of these three columns, but because the third column is just the sum of the first two columns, that third column is redundant in the sense that any expression that involves that third column could be rewritten in terms of the first and second columns. And as a result, the most efficient description is to say that the image of A is the span of just the first two columns. And in general, the way to identify this most efficient description is to look at the echelon form of the matrix and see where the pivot columns are. And you take the columns that have pivots, but you take the columns in the original matrix, not in the echelon form. But at this point, you might feel like the language that we're using, efficient versus inefficient, isn't really precise. And so it would be good to pin down precise definitions to talk about these things. So instead of talking about things being efficient, the formal mathematical term is linearly independent. And so a set of vectors is called linearly independent if it satisfies these two conditions. The first condition is that none of the vectors should be zero, because the zero vector is already sort of inefficient all by itself, so we don't want that. And the second, more interesting condition is that there shouldn't be any vectors on the list that can be written as a linear combination of the others. So if the vectors satisfy these conditions, then they're linearly independent. And if they don't satisfy these conditions, then we say that they're linearly dependent. So here are a few examples. So one important example is these standard vectors, e1, e2, e3. They're linearly independent. Obviously, none of them are the zero vector, and I think you can sort of look at these vectors and you can convince yourself that none of them can be written as a linear combination of the others, just because of the ways that the zeros and the ones work out. So this is an example that we'll come back to many times just because it's so nice and simple. So a second example is the three columns of the matrix that we were looking at on the previous slide. And these vectors are linearly dependent. And that's because of exactly the same reason that we discussed earlier, that the third vector can be written as the sum of the first two vectors. And here's another example of vectors that are linearly dependent. And here you can tell quickly that they're linearly dependent because one of the vectors is the zero vector. So that automatically makes it linearly dependent. But here's an example where the answer isn't so clear. None of the vectors is the zero vector, but just looking at the vectors, it's hard to tell whether or not you can write any one vector as a linear combination of the other ones. So what are the calculations that we need to do in order to figure that out? So there's a theorem that helps with this. And this theorem is really just a rephrasing of the conditions for linear dependence versus independence. The problem with the definition I gave you earlier is that it asks you to decide whether or not any one vector can be written as a linear combination of the others. So that makes it feel like you have lots of things to check, like is the first vector a linear combination of the second and third vectors? Or is the second vector a linear combination of the first and the third vectors? Or is the third vector a linear combination of the first and second vectors? So it feels like a lot of things to check. This theorem combines all of those things into a single thing to check. So what the theorem says is that a set of vectors v1 to vm is linearly dependent if and only if there exists a non-trivial solution to the system x1 v1 plus x2 v2 and so on is equal to 0. And what non-trivial means here is that at least one of the xi's is not equal to 0, because obviously if you set all of the x's equal to 0, then you would get 0. So non-trivial means some solution that's not the one where all of the x's are equal to 0. Okay, so I'll prove the theorem in a second, but before I do that, let me just say a little bit about what this does for you. So if we have these vectors v1 to vm, we can form the matrix, we'll call it A, whose columns are v1 to vm. Then, when you multiply A times a vector x, you actually get x1 times v1 plus x2 times v2, and so on. This is exactly the column picture for how matrices multiply times vectors. So comparing this with the condition that's in the theorem, we can see that we can check for linear dependence by looking for solutions to ax equals 0. If there are non-trivial solutions, then the vectors are linearly dependent. And if the only solution is the trivial one, then the vectors are linearly independent. And what's great about this is that solving equations like ax equals 0, that's what we've been doing since the beginning of the semester. We know how to do that. So to do it, we would put A in echelon form. For the purpose of this question, we don't actually have to go all the way to reduced echelon form. It's good enough to go to echelon form. And if it helps, you can imagine that there's an extra column of zeros representing the right-hand side of the equation. But because those zeros won't change when you do row operations, you don't have to actually write them out. And then you just have to look at where the pivots are. If there's a free variable, then the columns of A are linearly dependent, because that means you have more than one solution to the equation, not just the trivial solution. Whereas on the other hand, if there's no free variable, then only the trivial solution is there. And so the columns of A are linearly independent. So let's go back to the example that I showed you earlier. Are these three vectors linearly independent? Well, now we know that we can answer this question by making a matrix out of these vectors. And then we could do Gauss-Jordan elimination to put it into echelon or reduced echelon form. So I put it into Wolfram alpha, and what it tells me is that the reduced echelon form is actually the identity matrix. And the key observation is that there are no free variables because there's a pivot in every column. And that's all we need to know to conclude that the vectors are linearly independent. And I'll just emphasize that the issue is whether there's a pivot in every column. There doesn't have to be one in every row. So here's another example that illustrates that. Suppose you have these three vectors. These are four-dimensional vectors, and there's only three of them. When you make a matrix out of these vectors, and you go to reduced echelon form, this is the result, and you can see that again, there is a pivot in every column, and so the conclusion is that they are linearly independent. That extra row of all zeros at the bottom doesn't affect the answer. Okay, so we've been learning a lot of new concepts lately, and I think at this point it would be good to stop and think about how all those different concepts are related to each other. So subspaces are a really general notion which incorporates a lot of different ideas that we're interested in studying. In particular, the kernel of a linear transformation is a subspace, the image of a linear transformation is a subspace, and the span of any set of vectors is a subspace. But then on the other hand, a span is actually a nice way to describe a subspace. And so, for example, if we have a linear transformation and we want to describe the image of that linear transformation, a good way to do that is to give a set of vectors and say that the image of that linear transformation is the span of this set of vectors. But, as I discussed at the beginning of this lecture, the columns of a matrix will span its image. But this might not be the most efficient description because some columns might already be linear combinations of other columns, in which case there's a redundancy if we include them in the list. And so this is where linear independence comes in. A linearly independent set of vectors will efficiently span its subspace. And so really, when we have a subspace and we want to describe that subspace with vectors, what we're looking for is a set of vectors that span the subspace, but that are linearly independent. And so there's a term that combines both of these properties together, and that term is basis. A basis of a subspace W is a set of vectors such that the vectors span W and where the vectors are linearly independent. So conceptually, I would think of a basis as being a set of vectors that efficiently describes the subspace. So the concept of basis is going to play a pretty significant role in the theory going forward. And we're going to talk about it from a lot of different points of view, so you can just consider this a first introduction. But I'll point out that we can actually look back at some of the stuff that we've been doing previously, and we can see that we actually were finding bases, even though we didn't know it. For example, to find the image of a matrix, we found that a way to get an efficient description was to look at the reduced echelon form, determine where the pivots are, and then take the pivot columns in the original matrix. That process actually produces a basis for the image of A. And in a similar way, to describe the kernel of a matrix, we would do Gauss-Jordan elimination, solving the homogeneous equation, and use the free variables to write the solution as a span of vectors. Those vectors form a basis for the kernel of A. We were doing this already, now we just have a name for it. Okay, so finally, I promised you a proof of this theorem, so I'm going to do that right now. And just to give an overview, anytime you have a theorem that's of this form, where something is true if and only if something else is true, usually the proof will have two parts. One part is where you prove that if the first thing is true, then the second thing is true. And then the second part is where you prove that if the second thing is true, then the first thing is true. And it's common to use arrows like this to indicate the different directions of the proof. So in this direction of the proof, I'll start by assuming that we have a set of vectors that is linearly independent. And then I want to prove that there exists a non-trivial solution to the system. So you might need to look back at the definition of linear dependence, but there actually were two different ways that a set of vectors could be linearly dependent. One possibility is that one of the vectors is equal to 0. So we'll call that case 1. Suppose that vi is equal to 0 for some I. But this equation vi equals 0 is actually a non-trivial solution to the system. This is the solution where all of the x's are equal to 0 except for xi, which is equal to 1. And so we're done with this case because we found a non-trivial solution to the system. So the second way that the vectors could be linearly dependent is if one of the vectors could be written as a linear combination of the others. So if that one vector is vi, then we have an equation that vi is a linear combination of the other vectors. An important point here is that the right side of the equation doesn't have the vi in it because we're only using the other vectors. And accordingly, there is no xi coefficient. But now, if we move the vi to the right-hand side, then we get a 0 on the left. And on the right-hand side, we have a linear combination that involves all of the vectors, v1 to vm. Here, the coefficient of vi is -1. And so this is a non-trivial solution to the system. And in fact, it's worth pointing out that the reason we know it's non-trivial is because the vi coefficient is -1. So that coefficient is definitely not equal to 0. So that concludes the first direction of the proof. We showed that if the vectors are linearly dependent, then you can definitely get a non-trivial solution to the system. So now let's do the other direction of the proof. We assume that x1 to xm is a non-trivial solution to this system. Being non-trivial means that at least one of the xi's is not equal to 0. So let's pick out one of these non-zero coefficients. Then we could move all of the other terms to the other side of the equation. And then because the xi is a non-zero number, we can divide by it on both sides. And this gives us an equation that expresses vi as a linear combination of the other vectors. And that is exactly one of the conditions that tells us that the vectors are linearly dependent. And so that's it. That completes the proof. If you find this proof confusing, it's not a big deal right now, but I will warn you that in a couple of weeks, we'll start studying linear algebra in a more abstract context, where we will be doing proofs like this more regularly. So you can treat this as like a first experience with a proof like this, and as you gain more experience, this sort of proof will become more and more natural to you. Learning math is a little bit like how cows digest food. You have to chew on it for a long time, and sometimes you have to regurgitate it and chew it some more.